Hello everyone, this is Shen from Harbin Institute of Technology. The paper I present is comparative analysis of machine learning models optimized by Bayes algorithm for indoor daylight distribution prediction. My advisor is Han Yunsong, also from Harbin Institute of Technology. The presentation is organized in 4 parts: the background, methodology, result, and future discussion. Daylight is an important factor in architecture design. Well-designed indoor daylight conditions can improve occupants' health as well as energy saving. A common way to perform daylight evaluation is via simulation engine, such as Radiance and Daisy, but studies have found that they are not very popular in early design stage because intensive computing time often interrupts the design process. Rather, it's often used as a validation tool after design. As a result, the daylight improving potential was not fully explored. Many researchers have applied a machine learning-based method to evaluate building performance. Compared to simulation method, it sacrifices a certain degree of accuracy for speed, making it ideal for early design stage, when the exploration is more important than accuracy. But applying machine learning models to daylight prediction is a challenging task. The first is about the model's generalization capability. Previous researchers have used machine learning models to predict daylight into building environments. In design stage, the space can change frequently and drastically, so its prediction models must adapt to a wide range of conditions, not only constrain a certain size or orientation. The second is about model accuracy. Machine learning problems are often problem dependent. One algorithm is not guaranteed to work for everything. There are many available machine learning algorithms. Choosing which to use is difficult. Also, to get higher accuracy, we have to compare and fine-tune various model hyperparameters. The third is about the daylight prediction problem itself. Previous researchers mainly focused on predicting certain points or used average values to represent the whole room, using the spatial distribution information. Our method workflow consists of 2 parts and 4 steps, from data acquisition and preparation to model training and selection. First, a parametric simulation model was created in Grasshopper platform with the help of Honeybee plugin. The parametric model has 7 variables, which are also the inputs for subsequent machine learning models. The input range was set using a typical professor room. The output of the parametric simulation models is a 10 by 10 grid of UDI values. Note that the number of sensor points per room doesn't change with the room dimension, because machine learning models need fixed size of output. Letting hybrid samples method can create an equally distributed sample in multidimensional space, making it ideal for generating representative machine learning samples. After obtaining enough simulation data, we then process and split them into chain and test datasets. We did not directly take the UDI result from output. Instead, we subdivided it into 4 categories, which can preserve more detail. The dataset format has 7 input, which has been remapped to 120 range, and 400 output variables representing 4 UDI values at each sensor point. The algorithm we chose to experiment with are random forest, extreme gradient boosting, which are ensemble-based model, and multilayer perception, which is one kind of neural network, and spot vector regression is a very classic machine learning models. Given so many choice of algorithm, it's hard to determine which can perform better. Thus, a systematic method must be used to fine-tune and compare all models. We chosen the Bayes optimization method, which was proved to be much more efficient than brute force method and manual fine-tuning, and use mean square error as a performance metrics. Following the described workflow, we then train 30 different models for each kind of algorithm and pick out the optimal one. For training dataset, XGB and MLP models show very close results of 0.2 MSE score, with XGB models perform marginally better than MLP models. However, for test datasets, XGB models become significantly worse than MLP models. Apparently, MLP models have better generalization potentials on the task, which is what we're looking for. So the burst performance comes to 3 hidden layers MLP models with about 500 neurons per layer. The MAE distribution shows the errors are centered around 0, with 99% errors lower than 5. And by training models with different size of data set, we found that the model needs at least 300 samples to perform well. To further understand the error distribution in the whole space, we created an error map of each individual values by averaging the mean absolute error of all samples. Spatial distribution reveals that the error mostly occurred on UDI 2000 and UDI 2000 plus prediction. Also, the points near the window's opening and the corners tend to have higher errors. It may result from the fact that the change of window's width or height will drastically influence the illuminance values near the windows, causing them harder to predict. Next, let's see a concrete prediction result. A simple office room floor plan was created using only the proposed parametric models, so even if the original model is very simple, multiple models can be combined into more complex layouts. Comparing these two images, we can notice that the prediction model tends to overestimate the incoming daylight, and the result seems more smooth than the actual case, but it successfully captured the overall distribution characteristic. While this may not suffice for a detailed light design, in early design stage, this can still serve as a very efficient way to evaluate the daylight. This is how the prediction model can be used in action. Using a parametric model in Grasshopper, we can directly calculate the required input data from the geometry. Then, the connected machine learning models will make the prediction and send back the data for visualization. The prediction model only takes 300 milliseconds, so user can get the feedback almost instantly. In contrast, using simulation engines in this case would typically take about 3 to 6 minutes. So in conclusion, the experiment result shows that for daylight prediction task, the AI-based model is a better choice, and the proposed machine learning-based models can perform annual UDI prediction of the whole room with half second, which is advantageous. The main limitation of the current method is the absence of the urban context, so it does not work with a significant occlusion in present. In future, we will focus on adding surrounding environment as an input as well. The model presented in this paper is only a simple room model. In future, we will continue to extend the parametric model to represent more space. So far, we have successfully extended this parametric model to multiply windows and arbitrary windows position. That's all. Thank you for listening.